Here's a nice exercise based on the kramers-kronig dispersion relationships. Can you show the following? Say that you have a material without dispersion, so the real part of the refractive index as a function of the frequency is constant. If you have such a material, can you automatically show that that material has no loss? So pause the video and go and calculate some contour integrals. So we need to show that the material is lossless. So that basically means that the refractive index, or at least the imaginary part of the refractive index, is equal to 0. And obviously that also means that the imaginary part of delta n is equal to 0. And remember, delta n is the refractive index minus the refractive index at infinite frequencies, which is 1, which does not have an imaginary part. So this is what we need to prove, that the imaginary part of delta n is equal to 0. What are we going to use? We're going to use our friends Kramers and Kronig, because they tell us that the imaginary, let me get some more space here, that the imaginary parts of delta n, that can be calculated as an integral over the real parts of delta n. So we have minus 1 over pi, the principal value, the integral from minus infinity to plus infinity, and then we have the real parts of delta n as a function of omega divided by omega prime minus omega d omega prime. Now we also know that our material has no dispersion, so this basically means that delta n as a function of omega is a constant, so that we can bring this out of the integral. And if we're interested in showing that this thing is equal to 0, then we can just get rid of all of the prefactors, and then we need to show that the principal value of the integral from minus infinity to plus infinity, d omega prime minus omega, that this thing is equal to 0. So if you were stuck here deriving this particular integral, now could be a good time to pause again and try and calculate this particular integral over here. So let's have a look at a contour. So remember, of course, that omega is a real frequency. That's a fixed point here somewhere along the horizontal frequency axis, and omega prime is our integration variable. So an obvious contour to choose would be a small circle avoiding our point omega, and then a big circle here. So we're going to take the limits of big R going towards infinity, so that we can recover the integration bounds minus infinity and plus infinity here, if these things move apart towards infinity. And then we have a small semicircle here, C little r, and we will be taking the limits of little r going towards 0. So if we then draw some orientation arrows, this is what we should do. This looks very much like what we were doing when we were trying to derive the Kramers-Kronig relations in the first place, because then we also had an integral of f omega prime d omega prime minus omega. So you might be tempted to reuse what we did there, but there the very important difference is that our function f of omega here, in the limits of infinite frequencies, this thing should vanish, which is not what we have in our case. In our case, this is a constant basically, so this is not something that vanishes. So although this particular integral is derived from the Kramers-Kronig relationships, in order to evaluate that integral, obviously we cannot use the same reasoning as we did when we were deriving the Kramers-Kronig relationships in the first place, because the conditions are not fulfilled. But still, it's a rather straightforward integral to solve. So the only singularity is at omega, which is lying outside of our contour. So thanks to Cauchy, we know that the complete contour integral therefore vanishes. There's no singularity inside the contour. And our integral actually boils down to 3 different contributions. There's the contribution here along the omega axis, which after taking the limits will reduce to the principal value of the integral from minus infinity to plus infinity, the omega prime minus omega. So that's what we need to calculate. And this looks like 0, but there's some other terms that we need to add. There's of course the contribution from the little semicircle, and there's the contribution from the big semicircle. So if we somehow manage to show that these two contributions cancel, then we know that this integral is equal to 0, and then we know that we indeed have a lossless material. So our final challenge for the day is figuring out that these guys actually cancel. So pause the video and see if you can indeed verify that these two contributions cancel. They do cancel because of the small and the big limit theorems. So let's just calculate their contributions and see what's going on. So for the small limit theorem, remember, we first need to calculate a certain limit. So we need to calculate the limit when we approach the central point of the circle, which is in our case the limit at omega of the integrand, 1 over omega prime minus omega. So by the way, it's omega prime that approaches omega. But very important, let's not forget an extra factor, the integration variable times minus the origin of the circle. So we should not forget that factor. And then we see that these cancel, and it's basically 1 as a limit. So that means that for the whole contribution of our little semicircle up here, we have j, so that means that's the integral of c little r is equal to j times that limit, so we just calculated that's 1, times then the angle here, so we have an angle of pi, but very important, we traverse here c little r in the clockwise direction, whereas we know that by definition these integrals are taken positive in the counterclockwise direction, so we should have a minus sign here, or alternatively change the orientation of our angle to have minus pi there. So that's the contribution for the little guy. Let's now look at the contribution of the big guy with the big limit theorem. It's very similar in approach. We have another limit that we need to calculate, but this time a limit of omega prime going towards infinity of the integrand, multiplied by that same factor that people often forget. But the end result is the same. It's a constant, so regardless of which limit you take, it's again 1. So now, in this case, the contribution for the big semicircle is equal to j times the limit times the angle. And in our particular case, indeed, we have counterclockwise, so that's a positive angle. And lo and behold, we have j pi and minus j pi, so these guys cancel. So the conclusion there is that the integral that we need to calculate is 0, and therefore the final conclusion is that the material is lossless.